Start with kinetic molecular theory. What this means, this whole basis of kinetic molecular theory, okay, it's an entire theory, and it means that all particles of matter are in constant motion. So every single particle is in constant motion. Different types of particles, like gas particles, liquid particles, and solid particles, are in different types of motion. Okay, we kind of see that, right? I don't see this table moving, yet I know all of its particles are in constant motion. Okay, so there's different types of motion that we see depending on the state of matter that it's in. Okay, what we're going to be doing in this chapter, this is chapter 10 that has to do with kinetic molecular theory. We're going to be explaining the connection to the theory between gases, liquids, and solids. Okay, so we're going to look at how the theory applies to each of those main types or states of matter. So we're going to first start here with the kinetic molecular theory and how it pertains to gases. Okay, and we're going to talk specifically about what we call an ideal gas. An ideal gas is just that. It's ideal. It's living in a perfect scientific world, not necessarily in the real world, but everything that we're going to do in terms of study of these things will be in an ideal situation. Okay, so this is perfect chemistry world that we're talking about, and they follow these particular guidelines or stipulations. So an ideal gas is a hypothetical gas that fits into all of these assumptions that kinetic molecular theory puts out. Okay. Kinetic molecular theory has 5 main assumptions that we're going to talk about for gases, okay, and their state of matter. So we're going to talk about 5 ways that the kinetic molecular theory pertains to gases. All right, number 1, we're going to go through the 5 assumptions, okay? So the first assumption is that gas consists of a large number of tiny particles that are far apart relative to their size. Okay, so that's what the book tells us. It's a very kind of specific term here. But what it means is that gas particles are extremely tiny, okay, and we say they're far apart with relative to their size. Because they are so small, they might only be a centimeter apart, but that seems like a really long distance for particles that are that small. Does that make sense? Gas particles are very tiny and very spread out, okay, especially as compared to particles in a solid. Okay, they're very, very spread out in comparison. So this is just explaining the first assumption a little bit more. In a gas situation or a gas state of matter, particles are much farther away than in a solid or in a liquid, and basically the volume of a gas is mostly blank space. Okay, because gas particles are in constant motion, they're going to be continuously moving about within that container that fills them. Okay, so they're going to be always moving, but most of the space in that volume is going to be empty blank space. Okay. So this is the second assumption of our ideal gas or ideal gases in kinetic molecular theory. Collisions between gas particles and between particles in the container are what we call elastic collisions. All right? And elastic collisions are collisions in which kinetic energy is conserved throughout the entire process. Okay? So let me break that down a little bit. I'm going to give you a minute to write this down, and then I'll tell you what kinetic energy means. Let's talk about kinetic energy for a second. Does anyone know what the word kinetic means? Yeah, in motion. Okay, so this whole kinetic theory, kinetic molecular theory, means it's based on all of these particles being in motion all the time. So when you think of kinetic, you can think of motion. What it means when we look at an elastic collision is that when two things collide, there's no loss in kinetic energy during that collision. Okay, so if I have a particle and a particle, they're going to collide and they're going to bounce off each other at exactly that same speed. Okay, they could be coming from different directions. They'll be colliding in lots of different angles. They might not be straight on, but you can think of this kind of as like when you play pool. Okay, you can hit two objects and they'll bounce off each other. If it's a perfectly elastic collision, which in this kinetic molecular theory we're thinking perfect scientific world, an ideal gas, that means all of these collisions are perfectly elastic. So if they each come in with a certain speed, they're going to leave with that certain speed but in the opposite direction. Okay, so an elastic collision is when the two objects bounce off of each other. Okay, they don't stick to each other, they bounce right off. Okay? Number 3 assumption to do with gases here tells us that gas particles are in continuous, rapid, and random motion. They all possess kinetic energy. All right, and we said kinetic is meaning motion, so they contain energy in which they are in motion, or while they're in motion. Number 4 tells us there's no forces of attraction between gas particles. Forces of attraction between particles. Can anyone tell me the name that we know that describes that? Forces of attraction between particles. Yeah, Jonathan.
Polarity. Polar.
Close, close. Okay, that's really close. In the same area, polarity is the uneven sharing of electrons within a molecule. Okay, so that's within a molecule. What about things that attract an oxygen molecule and an oxygen molecule? What are those called?
Intermolecular bonds.
Yeah, intermolecular forces. Okay, intermolecular forces. Do you remember any of those types of forces? Yeah, Drew.
London dispersion.
Yep, London dispersion is one, and hydrogen bonds was our other. Okay, hydrogen bonds had a lot to do with polarity of molecules, and that hydrogen being attracted to the negative or the partial negative of that other molecule. Do you remember it a little bit? Okay, so in this ideal gas, in this kinetic molecular theory of an ideal gas, we have no attractive forces between molecules at all. Okay, these two don't attract at all. They're just going to keep moving, keep bouncing off each other with no attraction to stick together whatsoever. Okay, so this is an ideal gas. Gas particles act like billiard, okay, like pool balls. That's what I was saying earlier. They bounce off each other when they collide. They do not stick together. Okay, so there's nothing that's attracting the two together. They're just going to bounce off just like normal. All right, and so our last assumption with kinetic molecular theory says the temperature of a gas depends on the average kinetic energy of the particles. All right, and kinetic energy means the energy of those particles in motion. So think about it like this. The faster that you move, what's your temperature normally do? Increases, right? The more you move, the more that you get hot, right? Your body starts to heat up. That's the same thing. Okay, these gas particles, the faster they move or the more kinetic energy they have, their temperature will rise. Okay, and the gas laws that we talk about are going to look very specifically at those relationships between temperature, pressure, and volume. All right. We talked about ideal gases. Now we're going to look at what we call real gases. Okay, and these are real world type things. Again, when we do our calculations, when we look at kinetic molecular theory, we only deal with the ideal gases. Okay, we only mess with the ideal, but I'm going to show you the difference between the ideal and what happens in the real world. Okay, so gases, particles in real gases, they do have their own volume. Okay, it's not just all blank space. Real gas particles do have small attractions to each other, so there will be very small intermolecular forces. We know that intermolecular forces are much weaker in gas particles than they are in, say, solid particles or metallic type bonds, because those are very, very strong and tough to break apart, whereas gases are not difficult to break apart, right? They're already all spread out. Gas behavior in real world is mostly ideal, except when we have these three situations. So in the real world, we have pretty much ideal behavior for gases, except if we get to very low pressures, very high temperatures, or if we're dealing with nonpolar molecules. Okay, so in the real world, they act mostly ideal, except for these two stipulations and at these very specific times or situations. Back to an ideal world now. We're talking about kinetic molecular theory having to deal with liquids. Okay, so liquids in general, we know have a definite volume, but not necessarily a definite shape. So if we have a 2-liter bottle of something, we know its volume is 2 liters, but if we put that 2-liter bottle into a bathtub, it's still going to have the same volume, but it's not going to have the same shape. All right? Liquids have particles that are much closer together than gas particles, okay, because we know liquid has that very specific state where it can flow. Liquid is kind of the middleman or the second step between gases and solids. It's not quite as organized, I guess, as solids are, but more organized or more structured than a gas. Okay. Liquids have stronger intermolecular forces than gases. Do you think they have stronger or weaker intermolecular forces than solids? They have weaker intermolecular forces than solids. Very good. So in a liquid, we still have particles that are in constant motion, but we're not bound to one specific shape. Okay, just like the example I gave a little bit ago, if you dump a 2-liter bottle of something into a bathtub, you're not going to lose any of that volume, but you are going to lose that defined shape. Okay, so any liquids we know take the shape of the container they are in. So if the container happens to be a bathtub, it's going to look a lot different than if the container was a glass or a bottle or something like that. All right. So now let's look at solids for our kinetic molecular theory. This is where particles are packed as tightly as they can be. They form something that we've talked about in the past. When a solid becomes completely formed and set in its ways, does anyone remember what that's called? We talked about it with ionic things. Yeah, a lattice, okay, or a crystalline lattice. When that solid takes on its final shape, it takes on kind of a grid-like formula. Okay, those ionic solids will form what we call a crystalline solid. So when it finds that grid, everyone's at its happy place, kind of in a solid, it gets stuck there. Okay, it's held in place by those very, very strong intermolecular forces. Okay, so these solids have the strongest intermolecular force. So it seems odd to look at a solid, like especially like a piece of furniture or a book or whatever, and think about those particles being in constant motion, yet they are. Okay, they are not in a flying around, bouncing off the walls type of motion. They have what we call a vibrational motion. Okay, so they are moving back and forth very, very, very quickly, but with little impact. Okay, very, very small, obviously negligible motion. You don't see the table in front of you shaking back and forth. Okay, but those individual particles are in constant motion. Okay. So let's talk about kinetic molecular theory as a whole. We've looked at it in connection with each of those states of matter, but we're going to look at these properties for each of them. Okay. So each state of matter has very specific properties attributed to the kinetic molecular theory, things like pressure and temperature and volume for gas, and some other ones that we're going to look at for the other states of matter. What we're going to do now is we're going to make flashcards for these specific types and specific properties, I guess, of kinetic molecular theory dependent upon the state of matter. Okay, so I'm going to give you a list of the flashcards I want you to make. They're going to be in your book, and I'll explain that here in a second, but we want to play a game with them next class, so it's important that you kind of study them, get them memorized. It'll take you a couple minutes to make them, and then we'll study them today, and then next class we're going to play a little game with them. Okay, so if you don't know them coming into next class, the game will not be any fun for you. Okay? So our job will be to make our vocab of these words. They start on page 30. They go through page 339 in the book. I do want you to read the paragraph that goes with these words. Okay? So each of these is a specific property based on the kinetic molecular theory. I want you to work your way through the book. Don't be in the glossary. I want you to work your way through, read the paragraph, make a concise flashcard that has the word on one side, the definition on the other. Okay, and you also might want to put what state of matter that goes with. So a G or an L or an S for gas or liquid or solid. That way you kind of know if this is a property of a gas or a liquid or a solid. Okay, so here's your list that you need. You need to also read the text that goes with it. So this is going to take you more than 4 minutes to do.